finishing up our stuff on equilibrium. Our last topic is simply going to be Roman numeral 4, and we're going to just call it more on equilibrium. We're going to cover two things, KSP, as well as the common ion effect. Alright, so just more on equilibrium. And our first thing is going to be solubility product constants. Solubility product constants. Alright, and this is kind of one of those weird things where we learned solubility rules last year, such that chlorines, bromines, iodines are always soluble except with silver, lead, and mercury, but that's not really the case. Alright, our example is going to be lead iodide, and even everything we really say is insoluble to some degree in water dissolves, but the concentrations are so small that it's negligible. We basically say it doesn't dissolve. So even stuff that's insoluble, most of the time, is soluble, but really slightly. Alright, so solubility product constants are simply equilibrium constants for slightly soluble substances. Equilibrium constants for slightly or we're just going to call insoluble. Alright? We still call them insoluble even though we're kind of lying. Slightly or insoluble ionic compounds, let's say. Alright, so our example, like I just mentioned, is going to be lead iodide, and lead 2 iodide specifically. Alright? And it's a solid. If we put it in water, very few of these molecules, or really ions, are going to break up, but we're going to have a little bit of lead break up and a little bit of iodine. And it happens in this balanced equation such that we get one lead iodide in one lead ion in 2 iodide ions. Alright? When we write the KSP for this, alright, it has a little SP, so it's different than KC or KP. Alright? It's an equilibrium constant, but it's going to always have an SP, which means solubility product. And it's just going to be products over reactants. So in this case, we're going to have lead iodide ion, or lead iodine ions times iodine ions squared. And because this is a solid, it never makes it into our equilibrium expression. Alright? So it's just products, and we're not worried about our reactant. Alright? So a couple things we can do here. The first thing is we can use equilibrium concentrations. Using equilibrium concentrations, EQ concentrations, to determine, or let's say to find, KSP. Alright? And these problems might look like this. As an example, we might say, find KSP, or to say find the solubility product, if PB equals 1.2 times 10 to the negative third molar. Alright? And I'll probably say if PB at equilibrium is equal to 1.2 times 10 to the negative third molar. Alright? So if we set up an ice table for this, we're really going to have, we're going to do ICE. So our initial concentration, it doesn't matter if it's solid. Solids, again, don't have real concentrations, so it doesn't matter, or just not applicable. Alright, we have 0 of lead ion and 0 of iodine ion. This is going to change. Who cares how it changes? Alright, because it's not going to change much. This is going to change positive x, and this is going to change positive 2x. Right? So at equilibrium, we're really going to have x amount and 2x amount. But our problem tells us the value of x. Alright? Because it says lead at equilibrium is 1.2 times 10 to the negative third. Alright? So really this x is 1.2 times 10 to the negative third. Alright? And if that's what x is, then 2x is just going to be double that. So 2x is going to be 2.4 times 10 to the negative third. Alright? So now what we need to do is just substitute that into our expression. So KSP simply equals 1.2 times 10 to the negative third times 2.4 times 10 to the negative third squared. All right, and when we do that math, we get a really small number, which is 6.9 times 10 to the negative ninth. All right, so if we have really, really small numbers, what does that tell us? It tells us that the reaction is really, really reactant favored, which again is what we'd expect for something that is insoluble. We would expect that not much of it turns into product. All right, so the K makes sense with what we already know, and that's the way we would solve for KSP given equilibrium concentrations. The next thing we can do is we can actually find out using KSP, so we're going to go backwards, but using KSP to find the solubility of a compound. To find solubility. All right? And this might be worded like this. If, we're going to do an example, if KSP of calcium fluoride is 3.4 times 10 to the negative 11th, it'll say, what is the solubility? I think your book really says, what is the molar solubility? So it just wants it in moles. The molar, that too. Alright, let's see if I can scroll back down to where we were. What is the molar solubility of CaF2? Alright, so again, we are going to have balanced equation. So calcium fluoride, and it's a solid, dissolves into calcium ion and 2 fluoride ions. Okay? And it tells us what the KSP is this time. Alright, so again, if we set up an ICE table, ICE, alright, again, this is who knows, it doesn't really apply, this is 0, this is 0. This changes positive x, this changes positive 2x, and this changes x, and I kind of glossed over this on example number 1, but if this changes positively x, what's really happening over here? This is really changing negative x, or whatever this solid is, even though the molarity does not matter because solids stay constant. This is going to change very, very slightly, all right? In the end result, we really don't matter because we're going to say that it's still non-applicable, all right? But really these x's refer to this value of x, because as much as these change is as much as our calcium fluoride compound is really changing, all right? So this time we know KSP, so we're going to say 3.1 times 10 to the negative 11th equals, let's see what these are. This is going to end up being x, and this is going to be 2x. All right, so we're really going to have times x, and then this concentration is 2x, but notice we have 2 of them, so we're going to square that. Okay? So really, 3.1 times 10 to the negative 11th equals, if we take 2x squared, that's really 4x squared times x is 4x cubed. All right? So we're just going to factor or take 3.1 divided by 4 and then take the cube root of that. And we find that x equals 2 times 10 to the negative 4th. All right? And once we find that out, that x is not only how much these are changing positively, but it's really how much this is changing negatively. So that is your answer. Okay? That is the molar solubility of calcium fluoride. So just the reverse of what we just did. So kind of in summary, we can also talk about Q values when we're talking about KSP. All right? So we can use Q, which is just our quotient. Bless me. Use Q to determine solubility. All right? Will something dissolve or will it not dissolve? So a couple things. We're just going to have an A and a B. The first thing is Q can either be greater than KSP or Q can be less than KSP. So if it's greater than KSP, we might just say solid precipitates. Okay? Or we would expect to see cloudiness, chunkiness, milky. Okay? Let me mix two things. We would expect to see some precipitate. And that just means that if our Q value, whatever we mix, is greater than what KSP is, how is KSP, how is Q going to get smaller? Well, we are going to have to make our products larger. Okay? So solids are going to have to precipitate. However, if Q is less than KSP, that simply means that our solution is unsaturated. And if it's unsaturated, it means we can dissolve more ions into it. Okay? So our reactions will shift from right back to left. Okay? So we won't get a precipitate. That makes sense? Q is greater than KSP. Now, I think on A, I was thinking one thing and speaking another thing. So if Q is greater than KSP, Q has to get smaller. So how does Q get smaller? It shifts back to the left-hand side. And you're probably seeing me point to the right. I'm not sure how the camera works. But it will shift back to the left. And if it shifts back to the left, what is on the left side? It is solid. So we'll be making precipitate. All right? And if Q is less than KSP, it means that we want more product. And if we want more product, these are ions. So we can make more ions, which looks like we're not precipitating anything. All right? So there we go on that. The last thing we're going to cover today in this podcast is the common ion effect. All right? So it's going to be Roman numeral. It's going to be letter B, capital B. It's known as the common ion effect. Our next unit, which is acid-base chemistry, the common ion effect applies to buffer solutions. Right? So we'll talk about buffers next in our next unit. But the common ion effect is simply adding an ion that affects dissociation. And that is really tight over there. All right? Adding an ion that affects dissociation. It looks like it says apping an ion. There are no apps that I know of for common ion effect. So our first example is going to be pretty straightforward. It's just going to say, what is the concentration of hydronium ion of a 1 molar HF solution? Okay? So if we're talking about HF, this kind of goes back to hydrolysis. If it's a solution, we're adding water. All right? And HF is not a strong acid, it's a weak acid. So the H is going to team up with our water to make hydronium. And then we're going to have just fluoride ion floating around as well. Okay? So in this case, water, its concentration doesn't change. So our HF is 1 initially. We're just set up an ice table. Our hydronium is 0 to begin with, and fluoride is 0. And then the other thing you need for this is just our Kc expression. And Kc for this is 1.8 times 10 to the negative 4th. All right? So this is going to change negative x. This is going to change positive x, positive x. And this is going to be negative x, x, x. So really, what does this look like? Our Kc expression is simply x squared over, what's going to be, or I'm sorry, this is 1 minus x. Again, we're going to forget about our x this time, so it's really just 1. So Kc equals x squared. All right? So if we know Kc is 1.8 times 10 to the negative fourth, then x is simply the square root of that, or x is going to be 0.013 molar. Alright? And because x is hydronium, our hydronium concentration is simply that. Okay? Good enough. Alright, and our second example is going to be what is hydronium concentration what is hydronium concentration of a 1 molar HF solution? 1 molar HF solution with 0.5 molar 0.5 molar NaF added. Alright, so again, if we write just our formula again, that is really hard to read. HF plus water is going to yield hydronium plus fluoride. Our ice table is going to be super similar. We're starting with 1 molar here. This is 0, this is 0. And then the common ion is, what's true about sodium all the time? It is always soluble. So the sodium we could care less about, but notice if we have 0.5 molar, if we have 0.5 molar sodium fluoride, we really have 0.5 initially of fluoride ion. Alright? And again, if we kind of just write this real quick, sodium fluoride turns into a sodium ion and a fluoride ion. Okay? So if I have 0.5 molar of sodium fluoride, I really have 0.5 molar of sodium and 0.5 molar of fluoride. If this happened to be like magnesium fluoride, and we had a 0.5 molar solution, this, based on a balanced equation, we get 1 magnesium, but we get 2 fluorides. So if it was a 0.5 molar magnesium fluoride solution, notice our concentration of fluoride would really be 1 molar, because 0.5 times 2 is 1. Okay? But in this present example, it's just NaF, so it's just a 1-to-1 ratio. So this is going to change negative x, this is going to change positive x, this is going to change positive x. So at equilibrium, we really have 1 molar HF left. We have x of hydronium. And notice we're going to have 0.5 plus x. And again, we are assuming x is really small, so we don't have to worry about the quadratic formula. So this really is 0.5. Okay? Our K for HF, just like in the previous example, is still the same. So it is still 1.8 times 10 to the negative fourth. But now, our Kc expression is going to be a little bit different, just in the fact that it's going to be x times 0.5 instead of x all over 1. Okay? So Kc is 0.8 times 10 to the negative fourth equals x times 0.5. So this time, to get x, we're really going to multiply both sides by 2, or divide by half. So x now equals 0.00036 molar. Right? And if we compare that to our example number 1, which is 0.013 molar, having this additional fluoride ion very much affected how much of our HF dissolved. Okay, this can very easily be predicted with Le Chatelier's principle. Okay, and Le Chatelier's principle is simply going to say, and I'm going to change my color, if we add a stress, so our stress this time was we added more F. Okay, so if we're adding more product, what's our equilibrium constant going to do? It's going to shift this way to produce more reactant. Okay, so if we look at what our H3O is, okay, it is a product. So our first example is such that our first example is such that we made quite a bit of H3O plus. Notice we made 0.013 molars of it. Okay. Our second example, because our equilibrium shifted back towards the left, or towards the reactant side, we didn't make near as much product, and that's very easily seen in this number being over 100 times smaller than this value. Okay, so again, Le Chatelier's principle is good for predicting stuff, but we can use equilibrium constants to actually give us values.